This is a welcome back, everybody. Just because we're talking about right before the recording started, fun fact about the movie Alien. If you've ever seen it, if you haven't seen it, you should. It's an amazing sci-fi movie. A little bit gory, but if you know the premise, like I don't want to spoil it for anybody. Has everybody seen it or know the premise of Alien?
Yes.
Okay. The scene with the chest bursting alien. None of the actors and actresses, none of them were told what was going to happen. They were just told like there's going to be something that happens and you need to react to it. So that like when it pops out and like the blood spews everywhere, that's a 100% accurate description of them going, what the hell was that? Like they knew it was fake because it was part of they knew it wasn't like a real thing. Like the guy wasn't actually having like his heart burst out of his chest, but they did not know why that was happening. So that look on what's his face? I forget what the guy either way, that look on their face is 100% genuine of them being like in shock of what they just saw.
The car scene with the kids,
Uh-huh.
glass wasn't meant to fall. So
Oh.
that was genuine fear in those kids because it's an animatronic.
Yeah.
That was when I was like, oh, I'm getting started.
That's amazing. I mean,
Character.
awesome is not the right word because that would be awful, but also great that they got that on camera.
Right.
Heath Ledger walks out of the hospital, it's blowing up.
Yeah.
It doesn't blow up, and he's like, that's all real.
Yeah,
that's like blow up and it didn't, and then because the improv of his acting was amazing.
Oh yeah, excellent stuff.
I love that.
Very, very fun. Sorry to get sidetracked. So I said it right before we started recording. Sorry it took me so long and there were a few typos on the exam review. As you guys heard last week, so I was sick and my son got sick again. So my son has been sick for 3 weeks at this point. It's been a really rough time, both emotionally and physically, because I'm basically couch locked or holding locked because he wants to be comforted. So and then additionally, my wife had some medical problems that arose. So it's been a very, very busy weekend rather. So I was trying to get that stuff to you as quick as possible. So that's why there were a few typos. I fixed them and I'm pretty sure that like there's no typos in the answer key. Like I was typing it quickly because I didn't have much time. It was like right before he went down for sleep. So I should be all correct. But if you notice any mistakes or anything like that, please let me know and I can fix it. But feel free to use that in the aid of your study. Also, as I said, Paul's online notes has some really good problems on there. It's a good place to check for some stuff. The exam will cover 3.1, 3.3, 3.4, and 3.5. That's it. So 3.2, the mean value theorem is not covered on the exam. 3.6, we're not going to go over, and then 3.7 is going to be for the next exam or for the long quiz at the end of the semester. So yes, Paul.
3.1, 3.3, 3.4, 3.5.
That is correct.
Ain't your family sick now?
Say what?
Are you okay now?
Relative.
That's good.
His Phoenix is still his voice is still gone, and so he doesn't want to drink water because it hurts his throat, but he needs water to get better. So it's been a struggle. No clue what it is. Don't really like we took him into the doctor. There was just like, yeah, it looks like it's just kind of a sinus infection. He'll get over it. So I don't want to force antibiotics if I can avoid it.
Well, they should do a culture test
Probably.
before they administer, unless they're
Like they like
just do the rubber stamp antibiotic treatment.
yeah, they said like the person was like, I think we'll just call it good if it gets worse, like if the fever goes over this amount and go on. But either way, thank you guys for asking. So let's go ahead and start working on 3.5. It's legitimately, a lot of students think this is a very hard section because it's word problems, but really all it is just taking what you know about how to find increasing and decreasing and just applying it. So if you can understand that aspect and find the two equations necessary, everything kind of falls into place. So for this example, we just started a ranch, it's 200 feet of fencing, which is used to enclose a rectangular adjacent, two adjacent rectangular plots that share a fence. What dimensions need to be given to use, to enclose the maximum area? So the fact that it's going to be maximum, that's a dead indication to us that we're talking about an optimization problem and not a related rates problem. That's the most common thing that happens, is that students want to get those things mixed up. Now, the good news is for this exam, no related rates, right? Related rates aren't on this exam, so you don't have to have that confusion. But on the final exam, there might be one of each. There might be a related rates problem and there might be an optimization problem. Who knows? I haven't gotten that far ahead. I just haven't decided on the problems that I'm going to do. So knowing which one's which and how to apply which one is going to be important. So this one is going to be an optimization problem. So what are we trying to maximize? Area. Now this is a rectangular plot. Let's label these things because we don't know the dimensions. So let's call this X, and then we can call this Y. Then this is Y, this is Y, this is Y, and this is X, and this is X, right? Now you could, like, by the way, there's many different ways you could do this. You could have because a lot of students worry, you could have made this entirety Y. That is fine too. It will work out either way. It's just, I figured might as well do it this way. But just to be clear, it will be fine either way. So we want to maximize the area, right? So our optimizing equation is going to be the area of the rectangle, which we know is going to be, John Doe student writes X times Y. Why is John Doe student wrong? Because it's 2Y, exactly right. Tempted to say area's length times width and just go, okay, X times Y. But remember, the length of the base is 2Y, not just Y. So it's going to be X times 2Y, or more aptly, 2XY. More appropriately, just because of how we're going to do it. So notice that is an equation in two variables. In this course, we do not know how to maximize and minimize a function of two variables. So we have to be having some type of a constraint equation. Constraint equation. Okay. Typically speaking, when you're finding this stuff out, you don't know what to do. But what piece of information have I not used? The 200, right? We have at most 200 feet of fencing. So how can I create an equation using that 200 feet of fencing? Set what equal to 200? So that would be the area, and that would be like I'm glad you're like, that's a good idea. That's a good start. But the area is going to be measured in feet squared instead of feet, feet of fencing. 2x plus 4, Aston is exactly right. The amount of fencing needs to enclose that entire shape. So if we add up X fencing here, plus Y fencing here, plus another Y fencing, plus another X fencing, plus another Y, plus another Y, plus another X, that should add up to 200 feet of fencing. Because it can't be more than that, can't be less than that, right? So we have that 3x plus 4y has to equal 200. And let's add the justification there. Reason. We need to fence the entire plot. So adding up all side lengths needs to be 200 feet. And once again, 200 feet. So this is really, I should get rid of the chicken and the cow, maybe a chicken and a guinea pig. You have a guinea pig farm. Because 200 feet of fencing is not a lot of fencing.
You need H fence?
So what's up? Do you need each fence?
Reason.
We need two fence the entire plot, so adding up side lengths needs to be 200 feet.
Thank you.
Yeah, of course. So now we have a way of relating X and Y between each other. We can substitute Y in for X or X in for Y. It does not matter which one you choose. Every once in a while, there might be a better option. Every once in a while, there might be a better option, but it's not uniform. Not uniform, and you probably can do it either way. If you're getting really stumped on this, like trying to take the derivative of something, maybe try flipping it around. Maybe try solving for the other variable and see if that makes it easier. But either way will work. It's the great thing about this is that because of the constraint equation is a direct way to relate X and Y together, there is a way to relate each other. So no matter what way you decide to do it, you can do it. So from here, 3x plus 4y equals 200. I'm going to solve for x in terms of y, but we could do y in terms of x. In fact, maybe we should do y in terms of x. My argument for that is that 4 goes nicely into 200, whereas 3 doesn't. So that means that y is going to be 200 minus 3x over 4, or 500 minus 3/4 x. 50, not 500. Sorry. Thank you for catching that. $50 minus 3/4 x. So now we can plug that in for y and get that area was originally 2xy, but now it's going to be 2x times 50 minus 3/4 x, which is a much nicer equation to deal with. That is an equation now in one variable. And since it's in one variable, it's a function that we know and love. So we can take the derivative, find the critical values, and find where it's increasing, decreasing, or use the second derivative because we're not looking for increasing, decreasing. We're only looking for max and min. So we can use the second derivative test if we want, but the first derivative test is fine. That's the way I usually do it. So a of x is now 100x minus 3/2 x squared. Now, one way to verify that you know that this is going to have a maximum is knowing that this is a downward facing parabola, right? That's the equation of a downward facing parabola, which has a maximum right there, right? So we know it is going to have a maximum, but we still need to verify. So we need to find out where that critical value is. That being said, by the way, if there's a problem on the exam that has optimization on it, and you find the vertex of this line using Math 126 knowledge, you can do that too. If it was a quadratic, you could. But anything else, then we're kind of SOL. So A prime is going to be 100 minus 3x. So the CVs is just going to be x equals 100 thirds, or 33.33 repeating feet of fencing. So we're pretty sure that's the correct answer, but we need to be certain. Remember what I said before, when you're doing this, you have to verify. You have to verify. And yes, I know it's the only critical value, but realistically in real life, what you're going to get is probably many critical values, and it might not necessarily be that there is a maximum. And so that's a situation where you need to be certain. So we'll set up our sign chart. We can only have 0, right? Our x value could be at most 0 and at most 200 thirds, right? Let me explain that in just a second. 200 thirds, and here's 100 thirds. Because there's a constraint equation here, because we have at most 200 feet of fencing, the least amount that you could use on the x dimension would be 0, right? You could just make it a thin line. Or you could make it so that there was no width. And then that would be 200 like each, but you need 3 fences. So that'd be 200 divided by 3. So not too important. Mainly is just to make sure that this thing is a maximum. But if you plug in x equals 1, let's say, and then x equals 50, right? Because 200 thirds is not, yeah, 200 thirds, like it's a little bit less than that. I guarantee you, if you plug that into your function, beforehand, it will be positive, right? 100 minus 3 is going to be positive. So it's increasing here and then minus here, so decreasing. And that means we can put a big check mark to say that it is a maximum because it goes from increasing to decreasing. So by the first derivative test, the thing that we use to determine where there's relative maxes and mins by looking at like the slope or the hill, the valley. So max area when x is equal to 100 over 3, and that would mean that y is equal to 50 minus 3/4 x, which would be 3/4 times 100 thirds. (50 minus 3 divided by 4 times 100 divided by 3). So 25 feet. Oh, whoa, what is that? So notice that I didn't stop when I said x is equal to 100 over 3. That was not the full answer to the question. The question was, what are the dimensions? So technically speaking, I should say that the dimensions of the rectangle would be 100 divided by 3 feet and then 50 feet for the base because there's 2 y's. But because we have labeled our shape, we know what x and y are, so we can just leave it like that. We can say that x needs to be 100 over 3 feet or 33.33 feet, depending on what happens, and then your y value would be 25 feet. That would be sufficient because we have labeled what x and y are. Yes, Trevor.
Which equation did you plug your x values into again?
Oh,
A equals
so
x with the parentheses 50 minus 3 over 4x, or did you plug it into the derivative?
So I plugged it in when I found my x value. We know that our y value is related to x through this pink one. So you could either do it in here, that would be completely sufficient. Like this equation and this equation are the same version, but that's how I solved for y.
Well, wouldn't it be that A equals 2x parentheses 50 minus 3/4 is x?
So this is giving us the area. It's not giving us the dimensions. So the relation here gives us the connection between the two dimensions. Is that okay?
Mm-hmm.
Good question. Very, very good question. So yeah, we're going to plug it back into the constraint equation because that will give us the corresponding y value or corresponding x value. I guarantee you, if you want to feel free to check me on this. Solve for x in terms of y. I guarantee you, if you do that, you will get that y is equal to 25, and then and thusly x is equal to 100 over 3. Elizabeth.
So earlier you said you could have combined the y's like where you had them.
Mm-hmm.
And then you would end up having 2y.
Yes.
So how would the equation still, would we go through the same process or would there be like some differences?
Excellent question. So if we had decided, that's an excellent question. Excellent. Like if we decided instead of making each little subsection a y and making instead this entire thing to be a y, then our formula for area would just be x times y instead. And our constraint equation would be slightly different. It would be 3x plus 2y equals 200. Right? So same concept, just slightly different numbers. And when you solve it, when you do the exact same things, you would you would still get x equals 100 over 3, but you would get then that y is equal to 50. So this would be a good thing to just check to make sure. So instead of trying to solve it like this, change it to just y instead of y on the bottom. Change that, see that you get the exact same answer, just slightly different context. Instead of being 1/2 of the base, it's now going to be the full base. So the whole process is the same, just a small variation in the numbers. Very, very good question. Julie, do you have a question? Looks like you do. What we were talking about just then? Sure. So what Elizabeth was asking was like, if I had decided to make this different, if I had decided instead of making my measurements, I'm just going to redraw it down here. Instead of making my measurements like X, 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 and then Y, 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 if we instead just made this full thing a Y, the process would be the exact same. The area, we're trying to maximize area, so area would be X times Y here instead of 2Y, because there's only the base, the full measurement of the base here is just Y, if we were to do it this way. Then the constraint equation is the same concept, but instead of having 4 Ys now, we only have 2 Ys for the fencing. 3 Ys for the vertical aspect, 2 Ys. So your constraint equation would be 3x plus 2y is equal to 200. And we do the exact same thing. We would say y is equal to 100 minus 3/2 x. So very similar, but not the same. The other one was 3 divided by 4, but it was a different measurement. It's like slightly different. And then you plug this in for y here. You'd get a function in one variable. Find the critical values. Your x value will still be 100/3. I guarantee you. Your x value will still be 100/3. And then from there, you will you'll set it equal to 0, find the critical value, show that it's a maximum, and then find the corresponding y value by plugging it in there. And your y value in this case would be 50 instead of 25, because instead of being just one portion of it, it's the full thing now. So it'd be 25 plus 25. So just showing you that you can do this in a million different ways. There is no one right way. And just like before with my class, guys, remember, there's nothing wrong with messing up and starting over again. It could, you could try this a million different ways and not get the right answer, but then last time it just sparks some ingenuity and you figure it out. That's why with me personally speaking, when I'm taking exams, I leave word problems for last unless I know immediately right off the hand. Like if I read the I go through the problems, if this is my exam, legitimately on all my exams from when I was a student, I'd look at the first problem. If I know how to do it, start doing the problem. If I don't know how to do it, I'll put a dash next to it, or I'll just leave it blank, move on to the next one. If I know how to do that, then I'll do that one and go on. Like sometimes, though, I will read the whole exam first just to give myself a sense of what I'm going to be getting myself into. And if there's a word problem, I'll read it and let it simmer in the back of my head, because that's usually what happens. Your brain is working on it even if you don't realize it. So let it digest and then read it again. Like basically start over with new eyes to look at it again. Make sure you've gleaned all the information possible so that you can get the best start to the problem. That would be my recommendation for any word problem whenever you're facing one of those. So,
Are you having the x value into the 3x plus 4y or is that
you're going to plug it into, great question. You're going to plug it into the derivative. You're going to plug it into the 100 minus 3x, because remember, that's telling you where the function is increasing or decreasing. That's why we can draw these lines here, because we're saying it's increasing there, so it's going to be going up, and then it's decreasing past 100/3, so that means it's going to start going down. So our function will go up and then go down. So we're plugging it into the first derivative, the test values for the sign chart.
I thought you said that you plug it into the constraint equation.
That's once you've found the value. But if you're plugging in like the things that I've done in blue here, the test values, I plugged those in to the derivative. So so here's a prime and x. And then once you've gotten the x value, once you've verified that x value is a maximum, then plug that into the constraint equation to find the corresponding other value. So This one always reminds me of Mean Girls. If you guys remember that one scene, the math decathlon, it's like the sum of the first two numbers is greater than the four. Like that's what she's doing. That's what they're doing there. Was it what's the name of the character, like the main character in the math decathlon group? Is it Raj? I don't remember. It's been a while since I've watched Mean Girls. So like he gets that answer right away. Very impressive as mathematics. But find two positive integers such that the sum of the first number and twice the second number is 108, and their product is a maximum. So this is dealing with integers. So there's not really a picture that can be gleaned from it, right? There is a way you could visualize it as a picture, but that's unnecessary. That'd just be doing extra work. So what are we trying to find? We're trying to find two integers. So let X and Y or P and Q or M and N, whatever you want them to be. What do you guys want them to be? X and Y. So let X equal the first integer, Y equal the second integer. So what are we trying to maximize or minimize? Their product. It says such that their product is a maximum. So the optimizing, we're going to call it P for product, is X times Y. That's all it is. The product of these two things is X times Y. If it said the quotient, it'd be X divided by Y or Y divided by X. And that one would need like some clear distinction because either way. That's the optimizing function. But once again, that has two variables. So we know we're going to need a constraint function. There's got to be a way to solve for Y in terms of X or X in terms of Y. So what would the constraint be? Very, very good. X plus 2Y is equal to 108. The sum of these two numbers, the sum of the first plus twice the second is 108. Now notice that I didn't mention, because we don't know which one's which, we don't know, like we can just assume that the first one is X and the second one is Y. We don't know which one's bigger, but it doesn't matter. It doesn't matter. We just know that X plus 2Y is going to equal 108. That equation is going to allow us to know which one's going to be the bigger or the smaller one. So with that in mind, now we have a way to solve for X in terms of Y or Y in terms of X. Which one do you think we should solve for? Should we solve for X, meaning X equals stuff, or should we do Y equals stuff? X equals stuff is my go-to, because if I do that, then I don't need to solve for anything, right? I just need to subtract 2Y and I'm all done. So this would tell us that X is equal to 108 minus 2Y. But once again, if you want to hang out with your bros tonight and just pound a keg of Mountain Dew or whatever you kids do, and do this by, instead of solving for X, solve for Y, I guarantee you will get the same answers. So plug this in for X. And so now our product function, which was originally X times Y, is now X times 108 minus 2Y. Wait, sorry. Is 108 minus 2Y times Y. So P of Y is 108Y minus 2Y squared. I do this, it's not necessary to write P of Y, but I do that to mention to you that now we've got a function of one variable. It was in two variables. It was P of X comma Y equals X times Y. It was originally P of X comma Y is equal to XY. That was the original version of it. But we now have a way to represent it as purely one variable. That's why I write it as P of Y, just to signify to us, hey, now we can take the derivative and now we can find the critical values or value and go from there. So to find critical values, find the derivative. P prime should equal 108 minus 4Y Setting that equal to 0, P prime of y equaling 0 / DNE gives you that 108 minus 4y is equal to 0, or more aptly, y is equal to 108 divided by 4. Technically negative 108 divided by negative 4, but 27. Very good. So y is equal to 27. Now we're not sure. We will be sure, but we have to verify. So we're going to verify. Make a sign chart. And because these are two integers, we can make them anywhere we want them to be. So like we don't really need to have like specific bounds on our x, y values. But let's go ahead and verify. So here's y, here's 27. And so this is P prime. Let's choose y equals 1 and y equals 30. That seems fine to me. So if we're verifying that in P prime of y, if you plug in 1, you'll get positive. If you plug in 30, you'll get 108 minus 120, you'll be negative. So I'll even put that here just in case you didn't know. So plugging in into P prime y. So we're plugging it in and we get a max. Right, it goes from increasing to decreasing. So we've got this hill here. So we can put a check mark and say we did verify it. It is a maximum. So we know then that x is going to be, y is going to equal 27 and x will equal 108 minus 2 times 27, which is 54, I believe. 54. And since we have defined our variables, sometimes we define our variables with a picture. Sometimes we just define our variables outright with language, which is what I've done here. We've made x equal the first integer, y equal the second integer. So we don't need to say like the first integer is 54, the second integer is 27. We've described that in the problem. That's why I tell my students to define their variables, because we go back to my statement of how much work should you show. Imagine I'm an alien grading this. All I have in front of me is the textbook, the notes. I should be able to determine it based purely on that information. So you've defined it as let x equal 1, the first integer, y equal the second, and you're good. So that's why I recommend labeling them. Otherwise, it doesn't make sense. And if you don't label them, that's fine, but make sure that then your answer is like a statement. Okay, let's do another one. Unless there's any other questions on this one.
That says verify P1, right?
Verify and then colon and then P prime. P prime of y. And then y down here. Because that's our sign chart that we usually do. Now, granted, by the way, once again, you can use the second derivative test. Right? Remember, if your second derivative is positive at that point, it's a relative minimum. If it's less than 0, it's a relative maximum. So, I mean, if you take the derivative here, right, P double prime is -4. That's negative anywhere. Like, no matter what you plug into, it's going to be negative, which means that it's going to be relative maximum. So you can use the second derivative test, but I don't see a use in it, honestly, when you can just use the first derivative test, get more practice on that, because that's going to be how you graph stuff. So that's the reason why I don't really teach the second derivative. I don't really use it at all. I never have. But you can. Right? All right. All right, let's go ahead and do this one. So a box with an open top is being made by cutting 4 small congruent squares from the corners of a 20-inch by 20-inch sheet of tin and bending up the sides. How large of squares should be cut from the corners to make the box hold as much as possible? Now, that doesn't say maximize or minimize, but that's essentially what it means, right? You're going to maximize the area of the volume of this box. So we need to figure out what this thing is meaning. By the way, if you don't know, and this would be a situation where you can always ask me, if you don't know what congruent means, it means same size. So They're all gonna, like, it's not like we're gonna cut one side to have a big square and the other side to have small squares. All of them are gonna be the same size square. So let's draw a picture of a rectangular sheet. Well, I guess it's a square sheet. But that, and then we're going to cut little squares from the sides. The last one did not turn out well. And so, and what's going to happen is we're going to snip those ones off, right? And then we're going to bend it upward, because like what's going to end up happening is we're going to have this right here at the base. This right here is going to be the bottom. And then these little flaps here are going to make the other sides of the open top box. So it's an open top box because it's not going to have a top to it. That's what they mean by open top box. So when you cut off those things and you fold it up, you're going to get a box, which if you don't know how to draw, super fun thing to do. Can't handle that. Can't handle it.
Can't handle the truth.
That I have to. I'm sorry, guys. Hashtag sorry, not sorry to go with your Instagram stuff. You know, the Instagrams. Right, that's what you like. That's what you got. Like you do hashtags on Instagrams, right? Yeah, right. I know what it is, guys. Okay. Now the problem here is that we don't have any measurements here. We don't have any, like, remember, the size of the squares is what we don't know. So let's call that dimension X. We could call it S or any variable we want, but X is usually the go-to, right? But you can let your freak flag fly and do whatever you want, but I'm going to call these X. Absolutely, man. Okay. So, what dimension does X represent in the box? Like, yeah, but what's cut out? But once we fold it up, where does that X go? Does that go here, 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 here? Where? It's the vertical lines, because those are all the things that are folded upward, right? So all of the vertical dimensions are X's. In fact, I can even do that. We can even make these dashed marks here. So this ends up being a height of X. Right? But now the question is, what is the base? And the width and the depth?
Why?
We could call it Y, but we actually can do that quickly. So we know that this distance right here is 20. And so is this distance, because it's a 20 by 20 inch by 20 inch box, right? So the base is all those dotted lines in gray. It's hard to see it, but those dotted lines in gray right there, that's the base of the square, right? If we fold up all the square sides, then that leaves the bottom as the base. So what is that measurement?
The bottom length would be 20 minus 2x, right?
20 minus 2x, exactly right, on both sides. And granted, if this wasn't a perfectly square piece of tin, then maybe it was 24 by 20. So one side would be 24 minus 2x, the other would be 20 minus 2x. So what I mean is, it depends on which one it is. Like since this is 20 by 20, we only need to do it, that measurement is 20 minus 2x. But if this measurement here was 24 instead, then this distance would be 24 minus 2x. But as it were, this distance here is 20, the full distance of the tin, minus 2x's. One side, cutting it into it like that, and this side cutting into it. So 20 minus 2x. And this side, by a similar argument, is also 20 minus 2x. I'm doing it in two different colors, one in pink and one in purple. It's hard to tell the difference, I know, but I'm doing it in different colors just to signify that if the dimensions were not uniform, if it wasn't the same dimension, they'd have two different numbers there. One would be 20, one would be the other number, or whatever it is. So, and it doesn't matter which side you call which, because the way we orient this, this box can be flipped around. So, but we just know that one of these is the 20 minus 2x like that. And one of them is the other 20 minus 2x. So we want to maximize volume, right? So what is the volume of a box? Length times width times height. Yeah, base times width times height. So we're going to optimize V is equal to length times width times height, which in this case will be x times 20 minus 2x times 20 minus 2x. And we can FOIL this out if we want to, or we can keep it as is, however you want to write it. I'm going to FOIL it out and make it simplified. That's going to be x times 400 for 40, so minus 80x. And then plus 4x squared, or more preferably 4x cubed minus 80x squared plus 400x. Okay. Now notice there's only one variable here. So only one variable. So we don't need a constraint equation. Because it's already in one variable, we can find the critical values to find the maxes and mins, because we know how to take the derivatives and find critical values of one variable functions. The constraint, technically speaking, is that the bottom dimensions are y equals x 20 minus 2x and y equals 20 minus 2x, or z, I guess, if you want to call the other dimension a different number. Those are technically it, but you solve them right off the bat. Now, as a small aside, because we don't want to get a little carried away, I'm going to put a note here. I'm going to say that x has to be between 0 and 10. Why? This is giving us the domain of x. Just imagine it. You could either not cut squares at all, right? In which case it wouldn't form a box. So that you could make like 0.001 inch cuts if you really wanted to, and then fold up that tiny, tiny box. Or at the end point, if it was more than 10, you'd be cutting halfway through, right? You'd be cut like if you were at 10 or 11, you'd be cutting right here, which is past where the halfway point is. So you'd be trying to cut squares that wouldn't fit. You'd be demolishing the entire square. Do you see what I'm saying? So the maximum it could be would be 10, in which case then there would be no depth at the bottom. But regardless, it's between 0 and 10. And so like if x was equal to 10, or if x was greater than or equal to 10, we'd be making cuts larger than half the distance. Box's width, which can't happen. I only mention this because you're going to see something when we find the derivative. you're gonna get a critical value that's outside of 10. And that's a problem. Okay. Any questions so far? I want you guys to go ahead and find the derivative, find the critical values, and test it. I'm going to slowly fill in details. Boxes with, yeah, comma, which can't happen. And sadly, 12 does not go into into both. It goes into 160, but it does not go into 400. So probably going to just have to factor out a 4. No, 100, 100. We'll talk about it once we finish. And as a reminder, by the way, if you want to use if you're only finding critical values and you're not really needing to find intervals of increase and decrease, you can use the quadratic formula. I mean, in fact, you can even use the quadratic formula to find the critical values and then test it in the unfactored version of the function. But that's just one way you can do it. So you can use the quadratic formula.
To find the derivative?
To find the zeros of the derivative, if it's a quadratic, which this one is. Which largely our functions have quadratics. So, how did that turn into a line, you lion? So, you should get that 10/3 inch squares need to be cut. So when you take the derivative, as we said, unfortunately, 400 is not divisible by 12 neatly. 12 doesn't go into 400 nicely. So the most common factor is a 4. So I factor that out. You get 3x squared minus 40x plus 100 on the inside. And then you can factor it however you see fit. I did trial and error because that's the way it was beaten into my head when I was in high school. So that's the way I did it. So 3x minus 10 times x minus 10. And so you get the critical values, x equals 10/3, 10. And remember, 0 isn't one of them because 4 is by itself. It's a number. If it was 4x, it would give us a critical value at 0, but it's not. If it's just 4. So we only get 10 and 10/3, but 10 is not in the domain. If 10 was used, we'd be cutting the thing in half both ways. Like, let me just show you, just so we can visualize it. Here's your square. And you'd be making snips right in the middle. And so your base would be non-existent. You'd have a point for the base. You wouldn't actually have any dimension there. Alex, yes.
What was it before the critical value?
So the 4, there's a difference between 4x times 3x minus 10 times x minus 10. So by the zero product rule, the zero product rules say that one of those products is equal to 0. So in this case, either 4x equals 0, which gives us x equals 0, or the other two. But if we get rid of the x, then the zero product rule would say either 4 equals 0, which is ridiculous. 3x minus 10 would equal 0, which gives us that x equals 10/3, or x minus 10 is equal to 0, which gives us that x equals 10. So just as a reminder, because it's near and dear to my heart, it always kills me when I see a student make that mistake. I know it's an easy one to make, especially when you're on a time crunch, like on an exam, but please don't make it.
So like, if it's a constant.
Yeah, then it doesn't provide any zeros. That being said, not that being said. In addition to that, just as a reminder, remember e, the exponential function never equals 0. There's like at least 1 or 2 problems on the exam review that deals with e as a factor. And remember, e cannot equal 0, so it doesn't give you any critical values. E exists everywhere and it's never 0, so it doesn't give you any critical values. Yes, Leslie.
Why did you put it in between 0 and 10? I just put it in.
So, because I'm doing that because our domain is 0 to 10. Our x values can only be between 0 and 10. That's not wrong. It's not going to give you anything wrong by doing it the other way. It's just technically speaking, it should be from 0 to 10. This is just making sure that none of you guys are sleeper agents for UNLV trying to catch me and make a mistake.
Once you got the that at 10/3, plugged it in. How did you do that? Did you plug it in?
Yeah, I plugged it into the factored form of V prime. So this gets to a larger point that I want to reiterate. It's like what we're doing here is nothing different than what we did before. We're finding the derivative, setting it equal to 0 to find the critical values, and then find where the functions are increasing and decreasing to find the relative extrema, to find the maxes and mins. So it's like we're doing the whole same process. We're just adding on a cherry on top of taking the equation and creating it. Instead of being given the function, find the relative maxes and mins, it's create the function, then find the maxes and mins. Doing the exact same process. I get what you mean though. That extra step just seems to throw us off a little bit of what we're supposed to plug it into, but it's the same function, the same idea. Plug it into the derivative to see where it's increasing and decreasing, to find your maxes and mins. And then based on your verification, which we did with the first derivative test, which is this sign chart. The first derivative test is that sign chart that you make. If you go from increasing to decreasing, you have a hill, and that's where your relative max will be. Any questions? Any other ones? Okay, let's do another one. Upon imposing a coordinate system, a bug is traveling along the curve f of x equals the square root of x minus 8, and a chameleon is standing on the point 12, 0. Find the closest point on the bug's trajectory to the chameleon so that the chameleon has the best chance of catching it with its tongue, right? The farther away it is, the more chance the more time it'll take the tongue to travel, which means the fly will, or the bug will have more chance to sense it and fly away. So we're trying to find out when would be the minimum distance. And this gets us into a very, very annoying statement. Has anybody heard of the distance squared function?
Probably heard mentioned of it a long time ago.
So first off, let's draw a picture. So square root of x minus 8, that is the square root of x function that has been shifted to the right 8 units. That's like going back to our linear transformation stuff. So what this looks like is you only need the first, you only need the first quadrant. And it doesn't need to be perfect. But here is 8. And here's your curve. This is the curve y equals the square root of x minus 8. And then here's the point 12 comma 0. And then the chameleon is right here. There's your chameleon. And we're trying to, the bug is on this curve. So the bug is, let's just say right here. There's the bug. Got pinchers. Who knows what type of bug it is?
It's a beetle.
What is that? Like, can they eat them? Iguanas can't? Or is chameleons can't? Oh, I gotcha. Fascinating. Okay, so we want to minimize this distance, right? Let's call that D, which is the distance formula. You guys remember that? Square root of, so what is the coordinate point here? It's some unknown value, right? We don't know what it is. So its x value is going to be, let's call it x, and its y value is unknown. But we know that because it is on the trajectory of that line, its y value is the square root of x minus 8. So this is x comma the square root of x minus 8. Does that make sense? Because we're on that curve, our y value has to correspond to the square root of x minus 8. No matter what whatever our x value is, our y value will be the square root of that number minus 8 because we're on that curve. And the chameleon is at the point 12 comma 0. The distance formula is the square root of x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. You not remember that formula?
No, I said I didn't miss it.
What do you mean?
I've seen it a lot.
Oh, really? So we'll go ahead and compute this. But one of the things I'm going to talk about is what we call the distance squared function. So let's go ahead and plug this in. So you get the square root of x minus 12 squared. I'm going to do, this is my x sub 2, this is my x sub 1. This is my y sub 2 minus y sub 1. So plus y sub 2, which is the square root of x minus 8 minus 0 squared. So you get the square root of x squared minus 24x plus 144 plus x minus 8. Because the square root of x minus 8 minus 0, that's just the square root of x minus 8, and then you square it, cancel the square root. So we get this. The square root of x squared minus 23x plus 136. Yeah. Okay. So there's a fact in mathematics that the critical values of the distance function are going to be found by the distance squared function. Or more specifically, you can find the critical values of the distance function by looking at the distance squared. So ignoring the square root and just looking at the inside. Now, why is that the case? Think about it. If I found d prime, right? D prime of x, and you can still do it this way. It's just the distance squared function. You don't have to deal with the square root. But the distance squared function, you don't need to write this down, is going to be 2x minus 23 over 2 times the square root of x squared minus 23x plus 136. So when we find the critical values of this, right? If we were to find the critical values, you'd set the numerator equal to 0, right? Which is just the derivative of the inside. That's the derivative of the inside. So setting that equal to 0 will give you a critical value. And then also finding where this, the denominator, equals 0. But that's the distance, right? This right here is the distance. So setting this equal to 0 would mean setting the distance equal to 0, which can't happen, right? It's impossible. That would mean that the distance was 0. That would mean the point and the chameleon are the same point, which can't happen. And that's going to be like, that's going to be a thing that happens all the time, is that the distance squared function is all you need. Now, does that mean you have to do it that way? No, you can still do it this way. It's just you're putting more work on yourself. So the distance squared function is something that you can use. So I'm going to say, for these problems, the quote unquote distance squared function can be used instead of distance function. The distance squared function, you usually write it as d squared. D squared is equal to just x minus 12 squared plus the square root of x minus 8 minus 0 squared, which will equal x squared minus 23x plus 136. It makes things a lot easier to do it with the distance squared function, because this is just polynomial, right? A much nicer polynomial than the original version. So does anybody need me to reiterate why the distance squared function is going to be useful? It's okay if you do. Like, this is a weird concept, so I'm happy re-explaining it. And maybe explaining it in a different way now that we've seen what the distance squared function is. But once again, you can still use the distance function and take the derivative and find the critical values that way too. It's still valid to do it. It's just putting extra work on yourself. So once again, the reason for that is if you take the derivative of the distance, if you take d prime, once again, you get 2x minus 23 over this 2 times the square root of the inside. The square root of the inside equaling 0 would mean the distance is equaling 0, because this thing right here, this denominator, is the distance. And the distance can't equal 0. It's just physically impossible. There is no point on the curve, the blue curve, where the distance between the chameleon and the beetle will be 0. So it's a moot point. It's not useful. It doesn't give us anything. Does that make sense? So you can use the distance squared function or the distance function. And I will provide that formula. You don't need to have that one memorized if you don't want to. If this type of problem shows up, I'll say use the distance squared function or use the distance function to find the minimum value, okay? But I guarantee you can use either one and you'll get the right answer. Is that okay? Does anybody have any questions? So would you guys like us to use the distance squared function or the distance function? Distance squared. Going to be much nicer. So d squared prime of x is going to be 2x minus 23. So setting that equal to 0 gives you a critical value of x equals 23 halves. And so our x values, by the way, our x values start at 8 and they go on forever. There's no, like, it's not going to be that big of a deal, but just so we're clear. So here's 8. Here's 23 halves. Here's d squared prime. Here's x. Let's go ahead and test x equals 9. And x equals 23 halves is 11.5. No, yeah, 11.5. So 30. Whatever you want. What are we plugging this into? D squared prime. We're plugging it into the derivative to find the intervals of increase and decrease. So if you plug in 9 into this, you get 18 minus 23. That's negative. So it's going to be decreasing here. I should use a different color instead of blue because I've used blue above. X equals 9, plug that in, you'll get negative. So it's decreasing here, plug in 30. 22 times 30 is 60 minus 23, that's positive. So a min has been verified. Min verified. So the point, find the closest point. So X will equal 23 halves and Y will equal the square root of 23 halves minus 8, or more aptly, so 8 halves 16, so 23 minus 16 is 7 halves, the square root of 7 halves. And I guarantee you graph that you'll see as a fun little tidbit. Fun little tidbit is just if you want to figure out something, if you're curious about something, you'll notice that when you draw that curve, and here's the chameleon, here's the beetle, you'll notice that the tangent line at that point and the distance, the line of the distance line will be perpendicular. It won't be that case for any other point. It's just at that point, just a fun little observation. At least as far as I know, pretty sure. It's usually pretty. But once again, the distance square function, the regular distance function will work. It will give you the same answer. Yes. Nope, because it was only asking us for the closest point. So we don't need to look for any maximum point. And in fact, there is no maximum point, right? Because if you're trying to find a maximum value, right? You're trying to find the largest distance, but this thing goes on and on and on. Oh, wrong color. This thing goes on and on and on forever. So there's going to be a point, like as soon as you try and find a point, I can just put a point slightly farther to the right and it's a longer distance. But there are circumstances where, depending on the curve, there could be a maximum distance away. So a cool, like, a different question would be like, instead of figuring out the chances of success for the chameleon, the chances of survival for the beetle. And then that would be like, find the maximum distance away so the beetle has the most chance of surviving. So, any questions on that? Okay. Okay. Oh, yeah, I got rid of that one and that one. A small luxury chair company is trying to prepare for the holiday shopping. You know, every year in Costco, they bust out those like space age pods that you could sit in for like $12,000. Who buys it? I want to know. Who just goes into Costco? Yeah, I'm just gonna buy this $12,000 chair.
Rich people.
Yes, definitely. That would definitely be it, or a person who's unhinged, you know.
People spent more for it less.
True. Like where would you even put it? It's not perfectly like it wouldn't fit anywhere. I don't know.
Did you know a orange GameCube is like a rich person right now?
Wait, what?
The orange GameCube is super expensive.
The orange GameCube. Probably a rarity. Just like there's like a penny that it has a like the A and the
Yes, I know what you're talking about.
like there's a special penny from like 1990 or whatever that's like worth like 50,000. So look for pennies and sell them on the market. So this
We gotta look at the right market.
this large chair company is trying to prepare for holiday shopping. The Voodoo accountant determines that the revenue of the chair can be modeled by the function RQ equals negative Q cubed, because you know I have to use a Q cubed, plus 60Q squared plus 1,500Q, where R is measured in dollars and Q is measured in luxury chairs. Due to the size of their company, they can produce at most 70 chairs. So this is an optimization problem, but in fact, it's an absolute problem because we're working on a closed interval. they can either produce 0 chairs or they could produce 70 or anything in between. So working on closed interval 0 to 70. So extreme value theorem. It's an extreme value theorem problem. So going back to 3.1, find the derivative, find the critical values, test the critical values that are in your domain and the endpoints. The largest value will be your absolute maximum. The smallest value will be your absolute minimum, right? So r prime of q, derivative of negative q cubed would be negative 3q squared plus 120q plus 1500. And luckily for us, that does factor. We can factor out a negative 3 and we get positive q squared minus 40q minus 500. And luckily this does factor nicely, but you can also use the quadratic formula. You should get it to factor to negative 3 times q minus 50 times q plus 10. So our CVs are q equals 50 and negative 10, but we can't produce negative 10. Can't produce negative 10 chairs, that would be ridiculous. So we have our value. Now we don't even need to make a sign chart because we're working with the extreme value theorem, which the extreme value theorem tells you that if you're working on a closed interval, the absolute maximum and absolute minimums will either occur at an endpoint or a critical value within your interval. So that's why we know we don't need to make a sign chart. Is that clear? So we're just going to find r of 0. R of 0 will equal 0. Not r prime, r of 0. Because remember, we're talking about the revenue of the function. We're trying to find maximum revenue. So we're not going to plug into the derivative. The derivative is not revenue. It's the derivative of the revenue, which would be the rate of change of your revenue. R of 0 is 0. R of 50, just to save on time, don't want to plug it into my calculator. R of 50 will be 100,000. And then R of 70 is going to be 56,000. So it's asking us to find the absolute maximum revenue. So R of 70 is not the right one, it's R of 50. So max revenue when Q equals 50. Did I skip a page?
Yeah.
I don't know why I skipped a page. I'm sorry. That's why. Okay. Sorry about that.
You got 3.5 from and 3.7.
Yes, yes. Okay. So, oh yeah, of course. Go back to that one. So I was looking at the questions left and then I didn't scroll all the way back. So this is the next one. Let's go ahead and let's take our break right now. It's 12:40 or it's 12 it's 10:47, so let's come back at 10:55. So people watching the recording, take a break. Come back. We're back. So we're gonna do this one. A soda company is trying to maximize or minimize costs on their cylindrical aluminum cans. The can needs to hold 360 centimeters cubed worth of liquid. What dimensions should be used to minimize the amount of material? So think about what's going on here. It's a cylinder, right? So you want to minimize the costs, which means you want to minimize the amount of aluminum that you use, which is coming from the surface area, right? You have the surface area of the actual can. If you can minimize that, that will minimize costs. So what we do know is that the volume has to be 360 centimeters cubed. So we have this picture. We want to minimize. Now, luckily for us, I've already given us the formulas. We want to minimize surface area, but we want to maximize volume. Or sorry, blah, blah, blah. We want to minimize surface area, but we have a constraint on volume. So the optimizing function is going to be S equals 2 pi r squared plus 2 pi RH. And so you can use that formula without using it as a fact, but if you want to know how it comes from being, imagine if you cut off the circles on the top and the bottom, that's where we get the 2 pi r squared, because that's the area of two circles. And then the cylindrical sheet of paper has a height of h and a width of 2 pi r from the circumference of the circle. But that's the formula. And then the constraint is that the volume, which equals pi r squared h, has to be 360 centimeters cubed. So pi r squared h has to equal 360. Now, which variable do you think I should solve for? I would argue that do we want r equals or do we want h equals? I would argue h would be the best choice, purely because then I don't have to deal with square roots. That being said, though, it can still work the other way too. So I'm going to make it so that h is equal to 360 divided by pi r squared, and substitute that in wherever I see an h. And there's only one instance of an h. That's another reason to do it this way. Because otherwise, then I have to substitute in for r twice instead of just substituting one time. Does that make sense? So if I did it the other way, if I had solved for r, then I had to plug in, I'd have to plug in r here and here. But it's still completely valid to do it that way. Nothing wrong with doing it that way. Anyway, so our function now is purely in terms of r. S of r is going to equal 2 pi r squared plus 2 pi r times h, which is 360 divided by pi r squared. And remember, pi is just a number, just like you and me. And so it's okay to have it in a problem. You're in college, you're a number to us. I'm kidding.
Damn.
I'm kidding. I'm totally messing with you guys. Not here. Not in here, guys. Maybe to the university at large. Not in here, guys. Not in my heart. Okay. S of r, just simplifying it just a little bit, is 2 pi r squared. Pi's cancel, one of the r's cancels, so 720 over r. And just so we're going to be able, because we're going to need to take the derivative, right? Do we need to use a quotient rule on that? No, we do not. You can, but it's not necessary because that's 720 times r to the negative 1. Just as a reminder, so we don't need to do it that way. So S prime, S prime of r is going to equal 4 pi r minus 720 r to the negative 2, or more aptly, 4 pi r minus 720 over r squared. Okay. I need to set that equal to 0. And if I do that, what do I need to do? How should I solve? I'll set this equal to 0. slash DNE and get that 4 pi r minus 720 over r squared is equal to 0. And to solve that equation, we need one thing in particular. We need to find a common denominator, right? So we'll multiply the first term by r squared over r squared. So you get 4 pi r cubed minus 720 divided by r squared is equal to 0. Now, that is a difference of cubes, quote unquote. And if you remember SOAP, you guys remember same, opposite, always positive? For factoring differences of cubes? Well, don't worry, you don't need to. Because we can just solve this by hand. We can use the cubed root property. So either 4 pi r cubed minus 720 equals 0 or r squared equals 0. R equals 0, but that wouldn't make any sense. If the radius was 0, then the can wouldn't exist, right? Doesn't make any sense to say r is equal to 0. It's not wrong to include it, but it's just it would be a situation where like if you found that it was a minimum, then like you want to reflect on your answer and say, well, that doesn't make any sense. So here we'll just add 720 and divide by 4 pi. Get r is equal to this r cubed is equal to 720 divided by 4 pi. We'll take the third root of both sides and get that r is equal to that's a nasty number, but let's go ahead and find it. The third root of 720 divided by 4 pi, which is roughly 3.86 centimeters. We're not sure if that is going to minimize volume, but we have to check, right? So let's verify. So 0, and then here's 3.86. And we're doing S prime up here and R down here. So let's do R equals, let's say just 1. And R equals 4. If you plug in 1 into S prime, which is right up here, this is S prime. You can use this format of it, but that'd be a little bit more difficult to deal with. Not that it's wrong to do it that way, but like adding more work. Plugging in 1, the numerator is going to be negative. The denominator is going to be positive because it's r squared. R squared is always positive. So it's a negative over a positive, and that would be negative. So it's decreasing. Then plugging in 4. So 4 times 4 times 4 is 64. So 4 pi times 64 is a lot more than 720. So it's going to be positive over positive. So it's increasing. So the min has been verified. So we know what the radius is, which means we know what the height is as well. So R is equal to 3.86 centimeters. And H will equal, what was H? H was 360 divided by pi r squared. 360 divided by pi times 3.86 squared, which is approximately pi times 3.86 squared, which is 7.69 centimeters. The unspoken rule in my class, by the way, is round 2 decimal places. It's the unspoken rule. So what? 2 sig figs. Yes. What? 3 sig figs. Yeah.
Yeah, I was looking conceptually, doing the optimization, all that makes a lot of sense.
you mind explaining?
Yeah, I mean, like, I've always kind of like been inclined to word problems. It's easy for it's more tangible to read, but just like the actual work for this one, struggling to look at like find the derivative for this one.
Yeah.
When we had, I think it's the so you on the first line,
Mhm.
you compare the two pairs that are on the right side of the plus sign, right? So
Mhm.
2 pi r. 360, and then the pi and the r's cancel, you get 720 over r. That makes sense. When you then the next step down, I don't understand how it's hard.
Sure. Yeah, so we're gonna be taking, so the derivative of each piece separately, right? So the derivative of this would be 2 pi times 2r, which is why I get the 4 pi r. And then here to find the derivative of that, 720 over r is the same thing as 720 r prime. So if I were to take the derivative of this, I'm sorry, r, not r prime.
To the negative 30.
Yeah. So then it's going to be negative 720 r to the negative 2, which is negative 720 divided by r squared. Which is why it's minus 720, like, that's why that's there, which I converted to negative 720 over r squared. Is that okay? Is that right? Like, I want to make sure it's cool. Still don't get it. That's okay. So, are we okay with the fact that we can convert this to 720 r to the negative 1?
Yeah.
And then taking the derivative of that using the power rule would be 720 times negative r to the negative 2. So that's why it's negative 720 r to the negative 2. And then what I want to do is I want to convert this back to a fraction. So there's an extra added step here. This is negative 720 times 1 over r squared, converting r to the negative 2 to being back as a fraction. And then multiplying by cross, because 720 is that's 720 over 1. So that's where we get negative 720 over r squared. Is that okay? Yeah. Paul, yes.
That h equals 360 over pi,
And then 3.86 squared.
oh, okay, I thought it was 6.
Nope, 86. It's the R value. Okay. Any other questions on that? Okay. We did this one already. Oh, no, I did. Still need to be here. Or good. Just where are we supposed to be in the notes? And 3 is right there. We're supposed to go over 4.1. We're okay. I'm going to go ahead and do this one in a video, if that's all right. But we can just move on to 3.7 just to talk about the next step of our material. So do not worry about 3.6. 3.6 is a dead, archaic thing that's still required in our calculus classes for whatever reason. Basically, what it tells you in a nutshell is that the derivatives can be used to approximate values of functions. It's pretty fascinating. If we have some time during the break, I'll show you how you can use derivatives to basically create the function. So what it's saying in essence is, notice that if I know what the tangent line is, then if I want to know f of like this value, there's only a small distance in between, like distance and difference, right? So the derivative, the tangent line, is a much easier function to deal with. It's just a line. So plugging in a value into that would be a lot easier. Now, granted, the factor reason why that's archaic is that our calculators, crap, you can ask Siri, say, what is 3 squared plus 4.79 times, you could do it a lot quicker. So that's the thing. This used to be very, very useful when you were approximating things. Now it's kind of just a precursor to a much bigger concept called Taylor polynomials, which is super awesome, really cool stuff. If you want to know more about it, let me know. But anyways, antiderivatives. This is the next step in our process. Talked about how to take derivatives, but what about going the backwards direction? Is there a possible way? So we can take a function, take its derivative. Is it possible to take a derivative and go backwards? Right? How would we do that? So the most common application would be that when you're studying population model growths or things in physics and stuff, it's very rare that you're given the population model, but you know how fast it's growing. So like, you know that the population is growing at roughly like 12,000 bacteria every second. And can you do that to create a population model, which then can figure out what the population will be in 20 years or in 10 minutes or whatever it may be, depending on bacteria or bunny populations, who cares? So let f be a function that's ideally continuous. We are going to always see our functions being continuous. But in 182, you start to see functions that aren't exactly continuous. But it's very, it's not nearly as bad as it sounds. A function f, capital F, is called an antiderivative if f prime of x, capital F prime of x, is equal to f. So an antiderivative is a function where if you take the derivative of it, you get back the original function. And notice that I said an antiderivative, not the antiderivative. And that's because every function has infinitely many antiderivatives. Because think about it. The function x cubed plus 2x minus 1 is the antiderivative of 3x squared plus 2, because if you take the derivative, you get 3x squared plus 2, right? Because the derivative of the constant is just 0. But g of x equals x cubed plus 2x minus pi instead of minus 1 also is an antiderivative, because if you take its derivative, you also get back f again. In fact, any constant that you put there, pi over 2, 73, square root of 7, all of those things, when you take the derivative, they're just going to go to 0. They're just going to become 0. So all of those functions are antiderivatives. So the theorem that is saying is that if f is an antiderivative, then f of x plus a constant is also an antiderivative. So in particular, when you just add a plus c at the end of your function, that is the most general antiderivative. That is the most generic version of it, and not a specific one. So we call f of x plus c, capital F of x plus c, the general antiderivative. In most cases, we assume that we're talking about the general antiderivative. And so think about going backwards. What function will we need to take its derivative to get to x squared? What function would we need to take the derivative of? So it'd need to be a larger power, right? It would need to be like the power rule takes down the derivative power by 1, right? So like if it's x to the 4th, when you take the derivative, it becomes x cubed. So if we want to get to x squared, we get x cubed, but the derivative of x cubed is 3x squared, not x squared. So we need to counterbalance it with a 1/3. And then plus c. 1 over x. What function do we need to do? What function has a derivative of 1 over x? Natural log. Now, here's the tricky part. It's tricky. It's really tricky, really hidden. It's going to be natural log of the absolute value of x. Not just x. Good question. We'll talk about it in just a little bit. But this is the only one where it's kind of straight. The absolute value, it's the natural log of the absolute value of x. And I'll explain why in a second. What function would you need to take the derivative to get e to the x? E to the x. What function would you need to take the derivative of to get cosine? Don't say it out loud. Remember, sine and cosine are cyclic, right? Derivative of sine is cosine. There we go. So the antiderivative of cosine is sine of x. Well, because remember, the derivative of cosine is negative sine. But we're trying to find a function which when you take the derivative, you get cosine, and that's sine itself. What function would you need to take the derivative of to get secant of x tangent of x? Secant of x, because the derivative of secant is secant tangent. So antiderivative, oh, plus c's. That one might look familiar. We didn't do too much with inverse trig, but that's sine inverse. One over one plus x squared, that is tangent inverse. And this is the one where we're going to start seeing how we use this stuff. So sine of 2x. How would we find sine of the antiderivative? What function will we need to get sine 2x? Well, cosine, right? Cosine of 2x. That's going to be our first guess. But if you were to take that derivative, you would get -2 sine of 2x. So we're missing a minus sign that we need to cancel out. And we want it to be sine, not 1/2, or not 2. So we're going to need to put a 1/2 in front. Oh. So a -1/2. And then plus c. It's weird at first, believe me. And there's a more systematic way to do this stuff later on. But as it stands right now, the whole goal of this is to lead up to what we call indefinite integrals. And the thing we're trying to figure out is to see here is that antiderivatives are the undoing of derivatives. Undoing it. Because this is actually a very, very big aspect. So Newton's advisor, I can't remember his name, because of course it was a man, because this was the 1600s. But Newton's advisor was actually working on this. Newton discovered calculus, he discovered differentiation, and then I believe his advisor was looking into the opposite direction and the connection between the two, which is what we call the fundamental theorem of calculus. Very cool for later on. So back to the question that Julie had. Why is the antiderivative of of 1 over x the natural log of absolute value of x, right? So this is the way I'd like to explain it. If capital F of x was equal to natural log of just x, if it was just natural log of x, no absolute value, then it has a domain of 0 to positive infinity, right? Because it's natural log. Natural log only can be defined for positive numbers, right? But f of x equaling 1 over x has a domain of negative infinity to 0 union 0 to positive infinity. So if we're given f as 1 over x, if we're ignoring the antiderivative for a second, just ignoring this first fact, this function has a domain of negative infinity to 0, comma, or union 0 to positive infinity. So right off the bat, that doesn't work. They don't have the same domain. Ish. Whereas if you look at 2, g prime of x, or sorry, g of x is equal to absolute value of x. Has domain negative infinity to 0 union 0 to positive infinity. That function is defined everywhere except at 0, because natural log of the absolute value of -7 becomes natural log of 7, and that's defined. So the absolute value allows you to plug in negative numbers. Yes, Elizabeth.
Couldn't you just write it negative infinity to infinity?
So the 0 is a problem. So 0 is a specific point that cannot be included. If it was bracket, then we'd be fine. If it was bracket, we can include it. But to just spare you some details, g prime of x will also equal 1 over x. There's a little bit of work that needs to be shown there, and I'm happy to show it to you, but we're already past time, so I'm going to stop. But g prime of x has this, it is the same derivative. And remember, the general antiderivative is the most generic form of it. So it would be absolute value. That's the reason why this is more general. Yeah, the exam is on Wednesday. It covers up to 3.5. This stuff right here, antiderivative is not covered. 3.1, 3.3, 3.4, and 3.5. So not too much stuff to study, but it is like each section was pretty depth indeed. Like a lot of depth. Please use the review. And then also Paul's online notes has great questions on there, along with solutions that you can even start up. You can ask for the start of a solution, and then it'll show you how to start it and then give you next steps. Khan Academy, also another great option. I will see you guys on Wednesday. If you have any questions, feel free to come to my office hours. Otherwise, I will see you on Wednesday. Yes. Okay, I think sorry, it's been, I will,